Yeah, F19 and P31 NMR spectroscopy. In the like in the previous chapters, we discussed the about the C13 spectra. Now we are going to discuss the P31 and F19 spectra. So F19, channel P31 and F19, whose okay, magnetic momentum is it is not zero, so it is magnetically it is active, so it gives a spectra. The fluorine it is F9. It's okay. The magnetic moment I value is it is off here, and its natural abundance is 100%, and its sensitivity is 0.83. So these are the basic features of fluorine, and the fractional frequency of the instrument it is like 282 megahertz and 7.04 tau, and the reference compound which is used to record the F19 spectra is trichloro fluoromethyl trichlorofluoromethane. So trichlorofluoromethane, generally it is used as the standard compound, which along with the shampoo, where it is volatile and it gives volume F19 isotope. And the chemical shift, generally here, the chemical shift range of the F19 spectra is ranging from minus 280 ppm to 280 plus 280 ppm here. And here the chemical shifts of some of the derivatives of the like you see the carbonyl group which is attached to the fluorine. Its chemical shift is minus 70 to minus 20, and when the fluorine, three fluorines are attached to the carbon, so its value will be 40 at the plus 42 plus 80, and the difluoro, in that for trifluoro it is 40 to 80, but difluoro it is 80 to 140 with the uh, right. So the increasing of the number of fluorine atoms, it leads to the decrease in the delta values here, chemical shift values. For monofluor, it is 140 to 250. So you can see the scenario of the increasing of the decreasing. Okay, the ease of chemical shift values of the F19 spectra. And when the fluorine is attached with the aromatic substituent, then it's yeah, fluorine is a part of the aromatic ring. So we have that value 80 to 170, and the two flow. Okay, the two halogen atoms. Generally here, when the trifluoromethane, generally it is reference compound whose delta value is 0, and the fluorine with methyl. Okay, so fluorine, when the fluorine is attached with the methane, here's minus 271, and and like here the trifluoro, okay, methanol, its value is minus 78.6 methane. And here the table you can see the fluorine when it is a part of the various functional groups like alkanes, alkenes, carboxylic acid, okay, and carbonyl groups like ketones, and the interhalogens, okay, like fluorine, when it is attached to the iodine and okay, the chlorine, other halogens here. So that if you observe the tables, okay, so when the ethylene which is attached with one fluorine here, so value is minus 114, and when the ethylene two like two fluorines, right? So it is minus 81.3, like where the value is going to increase here. And in the carboxylic acid, trifluoro acetic acid, okay, trifluoroacetic acid. Uh, its value is minus 76.55. Okay, and there is trifluorocarboxylic acid and like trifluorocarboxylic acid in chloroform, sorry, carbon tetrachloride. It is minus 76 point. So based on that, okay, the solvent also, its value is going to, some slight difference will be there. And trifluorobenzene, it's minus 164.9. And well, with the difference, like the benzene, when it is at okay, one and like trifluoro, okay, methyl benzene, it is minus 63.72. So these are the values you can see. And okay, so the interhalogens like fluorine 2 bromines, its value is plus 7.38. And the two bromines with the two fluorines, its value is plus 7. Yes. Now the spin-spin coupling, like other magnetic molecules like carbon and hydrogens here. So here the F19, uh, it couples with other non-equivalent fluorine atom, and it couples with like other magnetic nuclei like carbon, phosphorus, and hydrogens, and it undergoes splitting here. Okay, so like in the C13 decoupled spectra, generally we won't observe the coupling, but here means splitting. In the F19 spectra, it undergoes splitting here, and yeah, the theoretical number of that is expected in same as in the H spectra. Okay, the spectra obtained, the appearance of the spectra is for example, with one example, like 19, proton couple, fluoric acid, it gives a triplet of quadrate, a triplet of quadrate. Since it couples with the directly matched CH2, okay, and it gives triplets. Okay. So fluorine first couples with the directly attached CH2 in a by fluoro, sorry, fluorine substituted acid. It so when couples with the CH2, no, the neighboring to non-equivalent protons, so it's use 2 plus n plus 1 like 2 plus 1, it is 3 triplet, 3 lines like triplet here. And each line of this triplet further split into a quadrate by coupling to 3 methyl protons, resulting in a triplet of quadrates. So here the proton decoupled F19 spectrum of fluorestone is only a singlet. So here you can see the fluorestone. in the application of F19 spectra. So it is often possible to achieve incorporation of fluorinated analogs, some amino acids into proteins simply by giving the fluorine containing amino acid in the diet of an organism. So, for example, here 4-fluorophenylalanine is incorporated into ribosomal proteins or growing uh, tetra amino cells when the amino acids is added to the culture medium. The similar fluorinated derivatives of phenylalanine, tyrosine, and tryptophan are incorporated into the lysosomes produced by avins by giving them fluorine containing amino acid in the diet. And that fluorinated acids, which are bases for smart sugar rings, fluorine substituted have been prepared and examined by fluorine. The study of fluorinated carbohydrates has been carried out by the F19 spectrum. Study the proteins here. So, protein since the generally exhibit a single fluorine resonance or a narrow band for resonance when the protein is denatured. So in the native conformation, loss shift effect would observed. So this is due to local differences in the individual environment of the fluorinated residues in the tertiary structures. And the drug analysis, so in the field of drug analysis also, this is and it can be used for quantitative drug analysis material uh, at the PPB level as possible. You can go with the example like 5-fluorouracil, which is an anti-cancer drug, so significant side effects, including cardiotoxicity. So these side effects were thought to be due to impurities in the drug. So by study of F19 NMR indicated many fluorine contaminating compounds. Subsequently, some of these impurities were identified, which lead to improved storage procedures. Similar calcium ion concentrations. So calcium ion is a universal messenger in cellular communication, and the intracellular calcium concentration is tightly regulated. The F19 spectra is helpful to study the cellular calcium ion concentration. And the F9 P31 spectra. So this is also having only one naturally occurring isotope, P31. Its NMR is very important to the organic chemist because many reagents like triphenyl phosphine, triphenyl phosphate, trialkyl phosphate, phosphonium salts, phosphorus ylides, means etc. These are contents of phosphorus, and it is also very important for the biochemist mainly because phosphorus is present in nucleic acid. like ADP, etc. Okay, some of the important properties of phosphorus, which is relevant for this cinema, which is discussed in the below. Like you see the basic feature of the phosphorus. If you see, the abundance is 100%, and it is magnetically active, and the ratio. And here the reference used in this P31 spectra is HTPO4, and chemical shift ranges is given like its range is around 530 ppm here. It's difficult to predict the chemical shift of phosphorus in various molecules here. 31 has rich literature of chemical shift data, and here is a when the phosphorus with trimethyl, its delta is minus 62. Okay, and for ethyl, triethyl, it is minus 20. So here, these are the values, delta values. And the applications of this P31 NMR. Yeah. Yeah, the phosphorus NMR is used to study the phosphorus compounds contained in soil, water, and other environmental samples. And the phosphorus transformation in agriculture, forest, and natural ecosystems can be studied. So with the modern high resolution instruments, even complex mixers such as extracts of biophosphonates use well resolved spectra. With the modern high resolution instruments, peak separation of a few hundreds of a ppm can be achieved for mixture of phosphorus compounds. It is easy to identification the possible since signal intensity can be relevant to the concentration. So by proper calibration procedures, qualitative analysis is possible for the reaction procedures. Bioextracts, metabolic products, pharmaceuticals, etc. The compounds classes that can be identified by P31 NMR includes the phosphonates, orthophosphonates, diesters, pyrophosphates, and polyphosphates here. So investigation of organic and inorganic forms of phosphorus in intact dairy mature sample is possible. Manure sample is possible. Variable temperatures measurements can be used in the studying equilibrium procedures such as those of conformational fluxional and tautomeric nature. The multi-pulse techniques in NMR spectroscopy. We pulse in the topic, it is studying editing techniques and 2D NMR spectral techniques and discussed. So after studying of this topic, so you can then have the knowledge of the molecular couplings and where the 2D spectra like okay in a spectra, depth spectra. So all these others knowledge you will discover. So we have seen in the previous sectors like H1NMR, P39, P31, and C13, F19. So the important use of 1D NMR spectra solve simple to moderately complex structures of organic molecules. So, however, it is not always enough to solve the structure of complex molecules. One of the most advanced technology in the NMR spectroscopy is the possibility of having several new pulse sequences by making use of microcomputers. This resulted in the development of variety of 2D NMR techniques. Pulses of various width and time intervals introduced between the initial magnetization and the onset of signal acquisition result in one-dimensional and two-dimensional spectra. So 2D designation for the 2D NMR does not refers to Cartesian coordinates, but it refers to the number of Fourier transformations resulting in the spectrum. So broadly speaking, 1D NMR, we have three stages like equilibrium period preparation, single pulse treatment, signal acquisition, and Fourier transformation of FID curves. So here the 2D NMR consists of main four stages. Between preparation and acquisition, there exists another period called the evaluation period. That means the preparation period is followed by two or more pulse with intervals depending on the experiment. With the preparation, the RF pulse and interval T1 here, evaluation period, and the acquisition period and acquisition T2, Fourier transformation. In 1D NMR, one frequency exists is present versus whereas in the 2D NMR, two frequency axes are present, two Fourier transformation. So in the preparation period, the nuclei reach thermal equilibrium. The preparation may consist of single pulse or a series of pulses to align the nuclei in some. The preparation period is followed by one or more R pulses which disturb the equilibrium polarized state. Is the period NMR receiver is not nuclear motion may to undergo some discrete motions which ultimately influence the signal. At the end of the evaluation, the existing magnetization is recorded in the form of the evaluation is increased gradually and for each T1 and and each may considered as a function of both time and period. So the lines in the spectrum obtained as a result of these Fourier transformations occur at the same frequencies as in the normal 1D spectrum, but the intensity vary with the changes in the T1. Large number of spectra are obtained at T1, different T1 values, and they are arranged in parallel arrays, one behind the other. Yeah, some terminology used in this 2D NMR spectra where the pulse angles, pulse width, and pulse delay. The angle by which M naught is net magnetization, is tipped away from the Z axis is known as the pulse angle. And the types of 2D NMR spectra. So here the 2D NMR spectra, basically it is two types here. J resolved spectra uh, and correlated spectra, rosy and cozy. Spectra, correlation spectra. So resolved spectra. So in 2D resolved spectra, the peaks are so spread that one axis present chemical shifts and the second axis present coupling constant. Resolved spectra again two types: homonuclear 2D and the heteronuclear 2D spectra heterocozy. Homocozy and heterocozy. Suppose not cozy. Related. So there are correlation diagram and the coupling interactions between the nuclei are presented in the form of contact spots. Again, they are further divided into two broad categories, homocozy and heterocozy. In homonuclear correlated spectroscopy, coupled interactions between the same type of nuclei like is before spectrum. These are again two types here. The correlation spectra involving in carbon-carbon correlations, inadequate and HMQC. Here is a brief classification. The results. So what lemma use accordingly chemical shift of different types of nuclei and coupling of these nuclei to the nuclei on the on one axis only. So this type of spectra allows the complete interpretation of simple molecules. So it becomes difficult to uh, unambiguous assign both chemical shift and coupling constant for corresponding for the compounds which give complex spectra. So why? Because for the overlapping of signals, the common occurrence of complex. So here the 2D result solves this problem. Spectra J resolves into second dimension. In 2D J resolves the chemical shift and coupling constants lies on two different axes. This allows one to assign delta and J values for giving given set of nuclei without any doubts and critical. Why? Because overlapping multiplets of nuclei with different chemical shifts are resolved in two dimensions. Resolved spectrum mainly two types here: homonuclear, food is resolved spectrum, heteronuclear. In the homonuclear, so we'll see when the spectral appearance of this by one example like ethyl chloride. So in this homonuclear, a doublet it shows two contact spots here. Triplet it three counter spots, quadrate four counter spots, pentate and with five counter spots here. If there is no coupling, the counter spot for this singlet appears on the zero line, coupling constant zero on F axis at the respective chemical shift values. There is a chloro ethyl chloride. So ethyl chloride where the okay, so it generally it gives quadrate, it gives triplet here. So for the quadrate, four lines. For triplet, it is three. If there is no coupling, so it lies in the zero line here. Yes, next, heteronuclear 2D resolved spectra. Heteronuclear 2D resolved spectrum is a 2D spectrum in which the coupling between carbon and hydrogens are resolved into second dimension. In the spectrum, C13 NMR chemical shifts are presented on horizontal axis, F2 axis, in the form of projection spectrum. And coupling of C13 and hydrogen are coupling constant values present on the vertical line in the form of contours. A doublet shows two contours, triplet shows three contours like resolved spectra here. In this particular ester, in the spectrum of ethyl acetate, and the cozy correlated spectra. Thermonuclear correlated spectroscopy is a 2D spectroscopy which gives hydrogen-hydrogen correlation connectivities in the molecule. Since protons are not directly connected, they are connected via carbons. So it is an indirect method and depends on the proton-proton coupling interactions. In these spectroscopic techniques, the coupling interactions between these protons are recorded and the diagonal contours are been uh, drawn. It's a spectrum of fluoropropane, propyl chloride here. And the heterocozy with the correlation between the okay the coupling constant and the chemical shift values here. And 2D inadequate spectra. So here, the 2D inadequate technique is one of the classic correlation experiment. So it was first devised for the determining the carbon-carbon correlation connectivity directly. So it makes use of carbon-carbon coupling to know the connectivity. So this experiment is the ultimate weapon for the uh, tracing the carbon skeleton, but it is least sensitive of all the 2D NMR experiments available. The least sensitivity is due to the reason that probability of finding two C13 atoms in adjacent position is very less because the probability is 0.01%. The intense signals that arise from this lone C13 are eliminated by the double quantum filtration and with suitable choice of delay time. So it can arrange that only the large one bond coupling greater observed signals and to establish the connectivity of the carbon-carbon. So we should start from some clearly assignable signals and run from its chemical shift, possibly in the F2 along parallel direction until peak was which correspond to the chemical shift of carbon, which is coupled and therefore connected. Then it was move against parallel with F1 from this point. Yeah. So here the example. Um, okay, so in this example where the spectra, 2D inadequate spectra in this indicating that so the parallel line A, okay, so which is shows C1 C2 connectivity here, and the line B is showing that the connectivity of C3 and C3. And one more line C is showing that connectivity of C3 and C4. Next one, NOSI spectrum, nuclear overhang spectrum. So a NOSI, it is a correlation spectrum which shows through space interaction via the nuclear overhangs effect. So it is useful for determining the protons which are closer to space but not closely connected by chemical bond. Yet, in this particular, so with these are closely connected protons here. Right? So the closely connected protons can be identified by this cozy spectrum. And the editing techniques of the C13, yeah, we have the three different techniques, FET, NEFT, and DEF2 spectra here. There is a APT spectrum of zero so BBD spectrum of zero where the BBD spectrum it is showing the okay, the number of carbons gives the number of signals in the BBD spectrum. But in the APT spectrum of geronium, so where the okay the CH3 and the CH protons are lies in the negative. Okay, so this appears in the sorry negative okay coordinate and yes CH2 and quaternary carbon. So appears in the above phase and these are in the below phase here. And inept spectra, inept is insensitive nuclear enhanced by polarization transfer. So this is useful experiment to enhance the sensitivity of less sensitive nucleus. In this method, polarization transfer occurs from a sensitive nucleus to insensitive carbon nucleus by the application of a special pulse sequence. Yeah. That's the optical rotatory dispersion body studies. This topic it explains the optical properties of the organic molecules and it explains the principle of circular birefringence, circular dichroism, photon effect, or the curse of rule, axial alpha and beta rule. So all the chiral molecules exhibit optical rotation, rotation of the plane polarized light called the optical rotation. Okay? The plane polarized light. So when an ordinary light traveling in all direction in pass to the nickel, when it is passing to the nickel prism, so it travels in one direction. That is called plane polarized light. The circularly polarized lights. When a plane polarized light is passed through a specially cut glass prism called the Robic, it travels in a sorry. presents rhomb. It travels in a circular fashion, which is called the circular polarized light. A ray of circular polarized light consists of two components, right circularly polarized light and left circular polarized light, EL. E or plus EL here. So here the energy is equal to the ER plus EL. Polarized light is equal to the both circular left and right circular polarized light. Say the okay, the equipment which is used in the block diagram where the light travels in the all direction, that is a multi-directional light. When it is passing through the equal prism, so it is converting into plane polarized light, and when it passes that particular uh, that is graft, so it is going to convert to it is when it is passed through that chiral medium, so it is giving the right circular polarized and left circular polarized. Yes. There is a symmetric medium. When the PPL is passed through the symmetric medium, the combination of ER and EL gives E. There is rotation of the polarized light, means the molecule is to be optically inactive. And when the light consists of two components, light circle polarized ER and through the symmetric medium, then the rates of transmission of ER and EL will be different. This phenomenon is called the circular birefringence. Circular two components of the light are absorbed by an asymmetrical extent. The resultant light elliptical polarized. This phenomenon is called circular birefringence. C. Automatic combination of C, B, and C is only and the occurs or occurs the result of optical rotation of a component with wavelength is called the optical rotation dispersion, and the curves obtained are called the verticals. The wavelength of absorption generally range from 700 to 220 nanometer. And verticals may be two types, like plane verticals and anomalous verticals. The plane verticals, they don't exhibit a peak or the trough here. They may cross zero rotation axis, plane verticals. These are two types again, plus and minus here. And anomalous verticals have peaks and trough. These curves are also known as cordon effect curves. Compounds with an absorption maximum in the region of measurement gives rise to the cordon effect curves. These curves are classified as plus and minus cordon effect curves, respectively. Depending upon peak or trough is reached first on passing through the long to shorter wavelength. It is a what it was here where it is not crossing the zero optical rotation here. that is plus verticals, minus where it is crossing the zero verticals, body optical rotation. And the octane rule. So it is an empirical rule was elaborated by Moffitt, Woodward, uh, Flynn, and in 1961. The rule permits the prediction of sign of quantum effect for optical active cyclohexanones from the structure confirmation and conformation. So to apply this rule, the carbonyl group should occupy the head of the chain or the board conformation. The system is viewed along the CO. The cyclohexanone system is oriented in the three-dimensional coordinate system with its origin midway between the CO bar. three orthogonal planes divide that cyclohexanone molecule into 8 octants. A vertical plane that is denoted with A. It is passing through the carbonyl oxygen C1 and C4, both axial and equatorial bonds on C4 lies in the plane. A horizontal plane B, it is passing through the carbonyl oxygen C1, C2, and C6, and the another plane C bisects the carbonyl group. Okay. So here this is the C here. Okay. The 8 octants are obtained which divided in two sets. Four front octants nearer to the observer, and another four are rear octants away from the observer. The front four octants are empty, therefore they may be ignored or discarded. The four octants, rear octants, are designated as given in this particular table. So you see for upper left, then for upper right, for lower left, and upper right, four rear octants. Here the substance in the R2 and L3, C2 axial and C5 axial. Contributes to the positive order effect is upper left L3, upper right R3, L2 it is lower left and lower right here. And the substrate R3 and L2, C3 axial and equatorial and C6 axial. So contributes to the negative carbon effect. Here we'll see with one example, like 3-methyl cyclohexanone. So with the methyl group is equatorial position, it exhibits the plus sign of the carbon effect. The sign of this carbon effect of the molecule depends on which of the octane that majority of substance falls into. So in case when two groups make opposite contribution, the group with more polarizability is more important. So you can see the polarizability order: iodine, then bromine, then chlorine, cyanide, phenyl, and alkyl group here. And application to this rule. So sign of configuration is given. Find conformation or plus 3-methyl cyclohexanone exhibits plus sign of cotton effect, and you find the conformation. So here is the molecule is given. No. So the chain form of this 3-methyl cyclohexanone, when it is flipped and it is interconverted to another form, and where the molecule is showing the positive and negative cotton effect here. For interconversion, we get the positive and negative. So this indicates that methyl group is in equatorial position. Therefore, equatorial conformer predominates, and it would have the positive cotton effect. And one more example, the trans 10-methyl 2-dicyclo, sorry, decalone. Trans 10-methyl 2-decalone exhibit positive sign of the cotton effect. Find its configuration. Here is a confirmation, here is a configuration. So you can assign the configuration and confirmation with the help of cotton effect. So here the given 10-methyl 2-decalone, it exhibits positive sign of the cotton effect. So configuration, you have to find what the configuration are in this here. Right. So when this is your molecule where the observer is seeing the molecule along with the carbonyl group here. Then where this okay, the methyl is okay, appears in the away to the observer here. So it is a positive cotton effect, and the positive cotton effect towards the observer nearer to that observer. It is showing that negative cotton effect. So it is S configuration structure here. So its configuration is the S. So we have two options like A and B. So the B1 is a correct confirmation for this one because A is showing the positive cotton effect here. Sorry, A is a negative cotton effect and B is a positive cotton effect. So the S configuration is correct one. And you can find absolute configuration. Next, axial 4-halo ketone rule, alpha halo ketone rule. So it is introduced in the 1957 by Dizarcy and Klein. And it is useful to the predicting the quantum effect of optical acute cyclohexanols containing the axial halogen. So very like primary condition, the cyclohexanol must consist the alpha halogen, except the fluorine. Fluorine will choose the fluorine or the bromine, except the fluorine. So the halogens like chlorine or the bromine, when it is located at the alpha position of the cyclohexanol form. So when the axial halocator rule is applied to predict the quantum effect of the compound in the model of the molecule, if the carbonyl group should occupy the head of the chain or the boat conformation, so closest to the observer viewed along the CO axis, like octet rule, axial alpha halogen to the right here. A cotton effect it will be positive. Means when the observer is observing the molecule through yes, when the observer is observing the molecule through this carbon, so the halogen is on the right side. It is if it is on left side, it is negative. So the axial alpha haloketone rule also it is stated as the effect of introducing an axial halogen from next to the ketone group of optically active cyclohexanol. It may alter the sign of the cotton effect cover of the parent compound. If there is a doubt whether alpha halogen is equatorial or the axial, so reversal of sign of this cotton effect upon alpha halogenation of the optically active bicyclic is a definite proof for that axial allocation of the halogen.